Hello and welcome you all to this lecture, and in this lecture we'll be discussing Cauchy-Euler equation. This is one part of this lecture and the next part will be the application. Okay, so initially we'll be discussing the Cauchy-Euler equation and relevant application of second order differential equation will start in this lecture also. Okay, so let's start with this Cauchy-Euler equation. The general form for equation of this type, see x power n dny dxn nth derivative, that is x power n y nth derivative, plus k1 x power n minus y n minus 1 y power n minus 1th derivative, okay, y n minus 1th derivative, plus k2 x power n minus 2 y n minus 2th derivative, plus so on. If you have this type of structure is equal with fx, so basically this is nothing but a non-linear type of equation, okay, non-linear equation and also non-homogeneous as well. So here you can observe one thing, these are the coefficients you are having, these are the coefficients, see x power n, this one k1 into x power n minus 1, k2 into x power n minus 2. So these coefficients are not constant. So far what we discussed is that the differential equation with constant coefficient, but here these coefficients are not constant. So it seems that you are having a different type of equation, that means the coefficients are variable. But see this equation, this particular form, it can be reduced to equation with constant coefficient. Okay, so this equation can be reduced to equation with constant coefficient, for which we already know the methods how to find solution for equation, differential equation with constant coefficient, correct? So we'll see the treatment. So for the time being, you just keep in mind that equation of this form, for example, if I just consider the next slide, for example, suppose if I have this type of equation, for example, see x2 d2y dx2 plus x dy dx minus 4y is equals to x square. Just observe this thing, x square here second derivative, x first derivative, okay, these are in multiplied form. So if we have this type of, or suppose another term is there, suppose x cube d3y dx3, for example, suppose, okay. So if we have this type of scenario where this equation can be reduced to equation with ODE with constant coefficient. What is the benefit of having constant coefficient? That means already we have the methods by which we can easily solve this equation, okay. So we'll see the method. See, if we have this type of equation, immediately we will substitute x equals to e power t. Just observe here carefully that we are substituting the independent variable. In place of x, we are considering e power t, so that if you take logarithm both side, t is equals to log x. We are having t is equals to log x. All right, t is equals to log x. Now see, whenever you have this dy dx, this dy dx, or d2y dx2, d3y dx3, this term you have to replace by dy dt, okay. And how we can replace this? For that, based on this substitution, we'll have the form, okay. So let's discuss that particular form. So we can consider this question itself and we'll try to solve this question, okay. So let's get started with the solution. Formally, I will do the entire solution so that you get a clear idea for this particular question, okay. So let's get started with the solution. So here we are substitute x equals to e power t, that is t is equals to log x, okay. Now dy dx, I need to substitute dy dx. So in place of dy dx, first you write dy dt dt dx. Okay, so from here dt dx, if you find, you will be getting 1 by x. So here immediately you can write this. You can write this one, that is 1 by x dy dt. That is, from here if you just cross multiply, you will be getting x dy dx is equals to dy dt. So wherever you have x dx, simply substitute dy dt. Okay, now next thing is what? See, second derivative. Okay, so second derivative, again here you differentiate both sides with respect to x. Okay, for example, so here you can see x d2y dx2 plus, here you are using actually the product rule, so dy dx, here d dt dy dt and dt dx, here you are using chain rule. Okay, so dt dx already you got 1 by x, so just substitute that quantity, that is 1 by x d2y dt2. Okay, so immediately what you are getting, see, x square d2y dx2 plus x dy dx is equals to d2y dt2. Now x dy dx, this term x dy dx, already you had x dy dx equals to dy dt. That means x square d2y dx2 plus dy dt, that is equal with d2y dt2. That means from here you can write x square d2y dx2 is equal with d2y dt2 minus dy dt. So this is another form you are going to apply. Okay, so wherever you have x dy dx, you are going to put this one, and x square d2y dx2 you are going to put this one. Alright, here you can observe that the independent variable in the right hand side, it is t. Okay, so immediately we can do this substitution. So what we are getting, see, x square d2y dx2, that's what here it is written. See, this one x square d2y dx2, it can be replaced by this. See, this is nothing but d square minus dy, and you know that d square means it stands for d dt. So basically here this is equivalent d2y dt2 minus dy dt, which we already got from here. Okay, similarly if x3 dx3 d3y dx3, if it is present, so immediately you have to substitute this. Okay, it is in the operator form where d, capital D, stands for d dt. Okay, now here you can change this, so d2y dt2 minus dy dt plus, here x dy dx, it can be changed by dy dt minus 4y is equals to x. What is x? X means e power t, so e power 2t. So here d2y dt2 minus 4y, that is e power 2t. So from the initial part you can either apply this operator forms, or you can just write down this substituted form, so that ultimately you are having d square minus 4y is equals to e power 2t. Okay, this is the form you are getting. Now the corresponding auxiliary equation you need to find, and then particular integral. So auxiliary equation, here you can write, suppose this auxiliary equation, it is given by m square minus 4 is equals to 0. So from here m is equals to plus minus 2, that is yc is equals to c1 e power 2t. Here see, independent variable is t, not x, plus c2 e power minus 2t, that is yc. Okay, this is yc we got. Okay, now next is what? Yp we need to find. So yp, let's find out yp. In the next slide I am going to, the next slide, that is yp. So what is yp? Yp is 1 by d square minus 4 e power 2t. So here you can see, if you are putting in place of d, if you are putting 2, you are getting 0 here. So what you need to do, multiply here by t, here in the lower term differentiate with respect to d. So you are getting this one. Now see, t by 2, 1 by d e power 2t. So t by 2, here 1 by d stands for integration, that way you can do, or in place of d you can simply put 2. So what you are getting, e power 2t by 2. So t by 4 e power 2t. This is your yp. So the general solution it is given by, general solution is what? Y is equals to yc, that is c1 e power 2t plus c2 e power minus 2t, plus here you got t by 4 e power 2t. Now back substitute t equals to log x, already we have taken that. X equals to e power t, that is t equals to log x. You can back substitute this quantity, c1 e power 2 log x plus c2 e power minus 2 log x plus here log x by 4 e power 2 log x, this quantity. Okay, now here you can c1 e power, you can apply the formula of logarithm, plus c2 e power log 1 by x square plus here but you have log x by 4 as it is e power log x square. So now if you further go for simplification, c1 x square plus c2 1 by x square plus x square log x by 4, that is y. So this is the final solution you are getting. See, this question, although it seems that equation with variable coefficient, but it has a pattern based on which we can convert it into equation with constant coefficient, and after that immediately we can solve. So this is one of the very vital topic of this ordinary differential equation. Alright, so this is Cauchy-Euler equation. Now we are moving to the application part of differential equation. Okay, so if you have any doubt or question, you can drop your query in the comment section. Now we are moving to that part. So here you have, see, application of second order differential equation, second order ODE. So application of first order ODE already we discussed in our first lecture. You can refer to that lecture of I think in this playlist you will find the first video where with the basic understanding we have considered the application as well. Now we are moving to the application of second order. Now here this is the first question we are having. See, example number 5, the damped LCR circuit is governed by the equation this L d2q plus d2q dt2 plus R dq dt plus 1 by C q is equals to 0, where L, R and C are positive constant. Find the condition under which the circuit is overdamped, underdamped and critically damped. Find also the critical resistance. This is the question we are having. Now see this question solution. L d2q dt2 plus R dq dt plus 1 by C q is equals to 0. So this is homogeneous equation. L, R and 1 by C, these quantities are constant, positive constant, it is given. So d2q dt2 plus R by L dq dt plus 1 by L into C q is equals to 0. Now this equation can be written as, see, this equation can be written as d2q dt2 plus R by L. This R by L can be substituted as 2p dq dt plus 1 by LC, it can be substituted as omega square q is equals to 0. So basically we are having R by L is equals to 2p and 1 by LC is equals to omega square. So why we are taking this? It has its own physical interpretation. From physics LCR circuit you will get a more clear idea. Okay, for the time being, see, in place of R by L you can take any constant. Okay, in place of 1 by LC you can take any constant, but to get a particular form we are considering this quantity 2p and omega square respectively, so that we are getting this quantity, that is d square plus 2p d plus omega square q is equals to 0, where d, it stands for d dt. Now see here, this auxiliary equation, that is m square plus 2pm plus omega square is equals to 0. So from here m is equals to, if you do the calculation you will be getting p plus minus root over p square minus omega square. This one you are going to get. Okay, now see, based on the nature, whether p greater than omega or not, p less than omega or not, or p is equals to omega or not, based on these three cases you have the different scenario. So for example, we can take case 1 as, suppose p greater than omega. So if p is greater than omega, so in that case the roots, that is m is equals to, in this case m is equals to minus p plus this quantity p square minus omega square and minus p minus root over p square minus omega square, it is there. Okay, so both the roots are real and distinct. So in that case the solution, because it is homogeneous, no particular integral part, so the solution, it is given by q is equals to, suppose a e power this quantity minus p plus root over p square minus omega square t plus b into e power minus p minus root over p square minus omega square t. Okay, where a and b are constants. Okay, arbitrary constants. Now see, in this case what you are having, this q, it is nothing but combination of e power this quantity and e power this quantity. Okay, so basically q is always positive. So this is the case for, when q is always positive, this is the case for over damping. Okay, over damping. And because of this condition p greater than w, we got the over damping situation. So what is p? P, as per our consideration, p is r by 2l, which is greater than omega. Omega means 1 by root over l into c. So if you further do the analysis, that is r greater than 2 root over here here, from here you can write R by 2L, that is greater than 1 by root over LC. If you further do the calculation, R is greater than 2 times root over L by C. So this is the condition for over damping. This is the condition for over damping. Alright. So this is over damping condition. Find the conditions under which the circuit is over damped. This is one part done. Now under damping part, P less than omega. If you take P less than omega, this case, so what you have, see, P less than omega. So if we consider this case, if case 2, that is P less than omega, so immediately what you have, the solution, the form of solution, what you have, see here, Q, it becomes, see, roots, that is M is equals to, we already got that minus P plus minus root over P square minus omega square. Now P is less than omega, that means immediately you are getting imaginary numbers, okay, both the roots are imaginary. So in that case, Q is equal to with e power, or let me write this m value, that is m is equals to minus P plus minus root over P square minus omega square. This was there. Okay. Now because P is less than omega, so you are basically going to get minus P plus minus I root over omega square minus P square. Alright. So from this consideration, what you are going to get, Q is equals to e power minus Pt A cos root over omega square minus P square T plus B sin root over omega square minus P square T. This is Q. Okay, so here you can see this is nothing but combination of cosine and sine function. So in this case, you have the period of the oscillation decreases, and this condition, it is for under damping case. This is the case for under damping. Period, it is gradually decreasing. So if you just try to draw the graph of this, starts from here suppose, and see the graph would be like this. It is gradually decreasing. So this is the case for over damping, under damping. And why you got this under damping case? Because of this condition, P less than omega. So P less than omega, it is nothing but R by 2L less than 1 by root over LC. So from here, R less than 2 times root over L by C. So this is the condition for under damping. Okay, under damping. And what is the next case? Case 3, it is P is equals to omega. So in that case, M is equals to minus P, and next part it will be 0 obviously. So two values are minus P. So based on this, you are getting Q as what? Q as A plus B T e power minus Pt. So this is the case where you have the critical damping. So this is the case for critical damping. So in this case of critical damping, R is equal with 2 root over L by C. This is the corresponding critical resistance. Alright, so this is the critical damping case. So thus we can determine the conditions for over damping, under damping and critically damping.